Hey everybody, it's Mr. N, and today we are going to talk about the mean value theorem, which we normally call MVT. So we will refer to this as MVT, and it's the mean value theorem. But before we begin that, let's get a little foundation, a little basis here. And we're going to talk about Rolle's theorem, because it helps develop the mean value theorem. But Rolle's theorem says, let f be a function that satisfies the three hypotheses. F is continuous on AB, and notice it's a closed interval. F is differentiable on the open interval AB, so it's continuous on the closed interval but differentiable on the open interval. And the third condition is that f of A equals f of B, which equals 0. In the Stuart calculus book, he does not state that f of A and f of B equals 0, but it really doesn't matter. Most books do state that they need to be equal 0, but as long as they are equal to each other, that's the concern here. Then there is a number c in AB, this open interval, such that f prime of c equals 0. So here's what this is saying. If I have my f of A value right here, right? This is A, f of A, and B, f of B, notice it equaled f of A. Again, it doesn't have to be 0. A lot of books will say that it's 0. Stuart says, no, it can happen up here. You can have the same thing up here. You don't need to necessarily have an axis, as long as f of A equals f of B, and I'm just drawing this simple curve to show you that. Okay, what we're saying is somewhere, if I connect A to B, whether I go up and connect them this way, like this, whether I go down and connect them this way, like that, whether I go like this in between, or whether I simply connect them, let's connect them with a straight line like that. Okay, no matter how I connect these, there is going to be somewhere where I am going to have a horizontal tangent, where f prime of c equals 0. So I end up with a horizontal tangent right there. Again, if I connected it like this, I would have had it down here, say, right? If I connect it some weird way, well, then I'll have a horizontal tangent here, I'll have a horizontal tangent there, I'll have a horizontal tangent there. So it doesn't matter how I connect A and B, as long as it's continuous, right? As long as it's differentiable on that open interval, and as long as f of A equals f of B, and again, most books will just say, okay, it's going to be 0, then somewhere along there, I will have a horizontal tangent that I can draw. So somewhere between A and B, the graph must flatten out. So let's do this example that verifies and tests Rolle's theorem. Okay, so we need to verify the three hypotheses of Rolle's theorem are satisfied on these three separate intervals, and we need to find f prime of c being 0. Okay, so first of all, let's do this. Let's take the derivative, because we need to verify that it's continuous and it's differentiable, and that f of A equals f of B, which equals 0 again. In this example, they will, but as long as they're the same. So let's go ahead and do this. So f prime of x, we end up with 12x squared minus 9. All right, so there's our f prime of x. So here, since f prime of x exists for all x, not just these intervals given, for all x, then it is differentiable on negative infinity to infinity for all reals. And continuous, we already know that it's continuous from negative infinity to infinity. Even the derivative is as well. Okay, so let's take a look at the first situation. 1. Is f continuous on the closed interval a to b? So I look at my f of x, it sure is. Step 2. Is f differentiable on ab? So f differentiable on the open interval a to b. Yep, I was able to take the derivative of it. So far so good. The two parts hold. Now, we need to find out if f of A equals f of b. So we need to do it again for each of the three intervals listed. So let's start with step 3, and we'll go on the interval from -3/2 to 0. Okay, so f of -3/2, when I solve this, I will get 0. So when I plug -3/2 in here, I will get 0. You can actually do something like this for this particular problem, and take out an x, and you're going to be left with 4x squared minus 9, and solve this, and you're going to get x equals 0 and plus or minus 3/2 if you wanted to do it that way. And you can verify that those are the zeros, and you will get zeros at each one of those values. So that means f of 0 will be 0 as well. So it works on this interval. What about the interval from 0? Oops, let's write that in nice. What about the interval from 0 to 3/2, and then the last interval from -3/2 to +3/2? Okay, on this one we said f of 0 was 0, f of 3/2 was also 0. This works. Here, f of -3/2 we said is 0, and f of 3/2, I will tell you this will be 0. Again, you could have done it this way and found the zeros. So yep, it holds. So Rolle's theorem holds for right here, part A, part 2, part 1, part 2, and for this interval it works, for this interval it works, for this interval it works. So it works in all three intervals, so Rolle's theorem is satisfied. Okay, so this right here, we showed all three parts of Rolle's theorem, and Rolle's theorem satisfied. All right, now they want us to find f prime of c equaling 0, so we'll go ahead and take that derivative, which we already did, set it equal to 0. I took the derivative over here, so this is just 12x squared minus 9, and I will take out this one. There's nothing really to take out to make it easier, so we'll just go ahead and solve for x directly, and we'll get plus or minus the square root of 9, 12, so you can write it as plus or minus 1/2 root 3. Okay, this is my f prime of c equaling 0 right there. All right, here we go. So now that you understand Rolle's theorem, you understand that there's got to be a horizontal tangent somewhere. Okay, as long as continuous and differentiable, when I connect these two, there's got to be a horizontal tangent. Okay, so that's the important part. Now here's what the mean value theorem tells us. Take a look, and I will explain this in a way that you will understand it. So, let f be a function that satisfies the hypotheses. F is continuous on the closed interval, f is differentiable on the open interval. So far, these two first parts are just like Rolle, right? Just what Rolle's theorem said. Then there is a number c, so here's the third part that's different, such that f prime of c equals f of b minus f of a over b minus a, or f of b minus f of a equals b minus a times f prime of c. This is just me manipulating it. What does this mean? What is f prime of c? F prime of c is a slope of the tangent. What is f of b minus f of a over b minus a? Do you remember what that is? That's a secant. That's the average. So if I have two endpoints, this is how I calculate an average. This is how I calculate a tangent. So that means the tangent is equal to the secant. We know the tangent as being instantaneous rate of change, and this is an average. So somewhere the instantaneous equals the average. How does this relate to Rolle's? Well, Rolle's over here said somewhere along it has to be flat, right? Look, if I connect A and B, these two are the same, they're parallel. So Rolle's theorem kind of gave us the foundation, and mean value theorem says, okay, it doesn't have to be equal. We can twist them and see that the secant will be the tangent. Wait a minute. What does this all mean? All right, here we go. Let me explain to you how we're going to do this. Suppose I get in my Ferrari. Yup, I'm going to get in my Ferrari and I'm going to drive 300 miles to Mathland. Yep, I'm going to Mathland. You might ask, what is Mathland? Well, it's kind of like Candyland, but there's math there. So, you know, someone like me, like a little nerdy, geeky guy, just loves it. So I'm going to Mathland. Okay, some people go to Disneyland, some people go to other places. I'm going to Mathland. So I'm going to get in my Ferrari. I'm driving 300 miles to Mathland, and it's going to take me 3 hours to get there. Oh boy. Yeah, it's a Ferrari. Come on. I'm going to drive pretty fast. I'm going to get there pretty quick. So 300 miles, it's going to take me 3 hours. All right, so here I am getting into my Ferrari. All right, pretty exciting, huh? Check out this interior. Okay, here we go. And let's take off to Mathland. All right, so you saw me getting in my Ferrari, and you saw me going to Mathland. Here's another, graphical representation of me and my Ferrari. And yeah, there I am, and I'm going to Mathland. So I'm going to start off right here, right? I'll start off right here at 0, start off at home, and I will say that this is my position, and this is the time, and over here, 300 miles away, and it took me 3 hours to get there, right? Time 3 hours, and I've driven, my position is 300 miles away, and this is Mathland, and it's got all sorts of pluses and minuses, and it's got integrals, which we'll learn later, and it's got derivatives. It's got all sorts of fun things here that those are the rides that are there. And here I am. I'm in my car. And am I just going to go boom like that real quick? No. So I have to start somewhere. I'm going to start at the house, and I'm going to leave my little house, and I'll get out of the driveway, and I'll start driving. Then I'll hit a stop sign, and then I didn't really hit the stop sign. I stopped at the stop sign, and then I got on the freeway, zoomed really fast, and then I part way there I had to pee. And then I continued on my way to Mathland. And then I got here, woohoo, I'm at Mathland, yay. Wait, let's draw what just happened. So I started off right here, and I'll kind of draw this, what's going on. I started off right here, and then I said I got out and I went slow, and then stopped at the stop sign, and then I zoomed along and I went really fast, but then I stopped, slowed down and stopped, and my speed right here, my distance, I should say, my position and time is pretty much, my position hasn't changed over the time because I went to the bathroom. So I stopped, and then I zoomed back along and I got to Mathland. All right, so right here I was going super duper fast. Right here it was an open road, and I was just zooming along. Look how much distance I covered. My position was close to that 300 in a short amount of time. I was zooming. I was going really fast. So let's kind of plot out what was happening. I had a starting point and an ending point, right? So I started here, and let's use this one, and I'll use the arrow key to show you where I'm going, and I ended up at Mathland over there, okay? So let's get rid of that, and now I'm just going to draw the line that connects from the 0 to the ending point, and guess what that line is called? Yep, that line is a secant. So if I draw this, I will get this secant that connected me from my starting position to Mathland. Okay, my curve in there is kind of a mess, but there it is. And this secant, you can tell me that I went a distance of 300 miles in 3 hours. So this was 300 miles, and this was 3 hours. So 300 miles in 3 hours gave me an average of 100, I can't do math right now, 100 miles per hour. That was my average. Okay, so this blue line depicts the average, which was 100 miles per hour. Well, was I going 100 miles per hour the whole time? No, I wasn't. It took me 3 hours, but maybe right here, I was only going 40. Maybe at this point, I was going, hey, it's a Ferrari. I was going 200 miles per hour at this point right here. Okay, this is the steepest tangent line right there. So I was probably going good 200 miles per hour right there. All right, but then I slowed down and, whatnot. But what happened? If I went at some point and I was driving and I was under 100 miles per hour, like over here, I was, maybe 40 miles per hour, and then over here 200 miles per hour, and then back to maybe like under 100 again at some point over there. So wait a minute, I had to cross the 100-mile-per-hour mark, right? So if I went from 40 to 200, at some point I had to go exactly 100. Do you understand that? So if I was going 40 miles per hour and I accelerated all the way up to 200 miles per hour, at some point I was going exactly 100 miles per hour. So at some point I was going the same as my average velocity. Wait a minute. That means at some point on here, the tangent line, and let me draw a tangent line, was equal to this average, which was 100 miles per hour. And maybe if I draw it, that's not it. Let's see if I can move this. It'll let me, oh, right there. Let me move it a little bit better, right there. So I will draw another one. Let's see. Is there another one that's parallel to it? Notice I'm using that word parallel. Whoa. So I'm looking for that parallel. Before I do that, let me clean something up here. This looks a little jaggedy. I want it to be smooth, so just kind of smoothing this out right there. We could do that. Okay. All right, and it's okay if it's jaggedy, actually, but it's fine. But in any case, let me draw another parallel. So I'm going to draw this. Oops. I need the line tool. Come on, the software. Come on, work with me, software. And here is my parallel. And let's see where I can move this parallel. And right there. At this point, I have a tangent, and we'll kind of move this so that it is a little bit better as a tangent right there. So I have 2 points from this graph, 2 tangents that are parallel to that secant. So here's that tangent, here's the other tangent, they're parallel to the secant. What does that mean? That means right here, at this point, my instantaneous, right there, at that point, my instantaneous equaled 100 miles per hour. Right here, at this point, my instantaneous equaled 100 miles per hour. So that told me at some point, mean value theorem, my mean value was 100. So I could have sped up, I could have slowed down, but when I went from 40 miles per hour all the way up to 200 miles per hour, that meant I had to cross through the 100 mile per hour mark, and so my instantaneous velocity was 100 miles per hour, and at that point, my instantaneous equaled the average. And that's all mean value tells you, is the instantaneous will equal the average if you're on a continuous closed interval that's differentiable on that open interval. So here's another example. So kids, it's really not that hard when you really just break it down into what it really means. So again, let's take a look at this one. Here is my starting point. Here is my ending point. Here's my curve in between. Okay, so then I draw the orange line, which is the secant, and then I take a straight edge, a ruler, whatever, and I can find the tangent. We're going to do it mathematically, not with a straight edge or ruler, but here's a tangent line. In fact, I have another one. Right here is another tangent line, right? So at this point right here and at this point right here, those 2 points, my instantaneous, which was the tangent line, equaled my average. Here's another one. Here's point A, here's point B. So notice it's taking Rolle's theorem and saying, okay, Rolle's theorem was these two had to be equal on a flat curve. And now they could be twisted like that, but still when I connect these two, I'm going to have a point where I'm going to have something parallel to it. And right here, that point, the instantaneous equals the average. So that's what the importance of Rolle's theorem in developing mean value theorem was. And right here, this is the tangent line to this point, and at this point, my average equaled my instantaneous. So MVT states at some point between A and B, there is a tangent that is parallel to the secant, and right here, that is a tangent that's parallel to the secant. You can take a look at this website. Sometimes it works, but it used to work off Java, and I know a lot of things don't use Java anymore, so it may not work, but it's a cute little demo that shows you that. Well, what's the importance of this? The importance is that such a number C exists, and it's sometimes called the existence theorem. It also enables us to obtain info about a function from its derivative, and that's what we're going to do. We're going to take the derivatives and get a lot of information about a function. So right here we have a theorem: if f prime of x equals 0 for all x in the open interval of ab, then f is constant on ab. The corollary is if f prime of x equals g prime of x for all x in the interval a to b, then f minus g is constant on a to b, and that is f of x equals g of x plus c, where c is a constant. All right, so these two we'll use in a little bit, this theorem, but for now, let's just go ahead and do one example of Rolle's theorem. Again, we're going to do more examples of MVT, and I have another video that I will link that is more MVT examples of how you'll see it and the situations where it'll come up. So for this problem, it says verify 3 conditions of hypotheses of Rolle's theorem are satisfied for f of x equals 2 sine 2x on 0 to 1/2 pi, which is pi over 2, then find a suitable c that satisfies the conclusion of Rolle's theorem. Okay, so Rolle's theorem. Again, let's review what we have to do. We have to do 3 things. The first thing is we need to determine if f of x is continuous on this from 0 on the closed interval. We want this to be closed to pi over 2. Is it continuous on this closed interval? Yes. This sine of 2x, if you graph it, it will be continuous. Is f of x differentiable on the open interval from 0 to pi over 2? Let's go ahead and take this derivative. F prime of x. This equals cosine of 2x times 2. So we'll just say 2 cosine 2x. So yes, it's differentiable on this interval. So I could plug in 0, I could plug in pi over 2, and I will get an answer for this whole thing. Okay, so now we have to do step 3. Okay, now we need to find f of 0 and f of pi over 2 and see if these are equal. So let's go ahead and do that. F of 0, when I plug in 0, I will get the sine of 0, which is 0. When I plug in pi over 2, I will get the sine of pi, which is also 0. So f of a equals f of b, and like how a lot of books say, there's 0. Okay, so Rolle's theorem holds right there. And now I need to find a suitable c that satisfies the conclusion of Rolle's theorem. Okay, to find that suitable c, I need to take this derivative, f prime of x, and set it equal to 0. So 0 equals 2 cosine 2x. Solving this, I will get multiple values, right? Because I'm looking at all values, but I want to be concerned with the interval from 0 to pi over 2. That's the interval that I am concerned with. So, over here, solving this, I get at, I'm basically looking for, this divides out, 0 equals a cosine of 2x. So I'm looking for a value of x that gives me 0. So at pi over 2, that I'm looking for the cosine to be 0. That happens at pi over 2 and 3 pi over 2 and so on. But I only need this in this interval from 0 to pi over 2. And that will occur for an x value of pi over 4. Because if I plug in pi over 4, right, 2 times pi over 4, this reduces out and I get the cosine of pi over 2, which is 0. And that's what I'm looking for. So you could put, you're not going to put plus k times 2 pi or in those rotational effects, because I'm only concerned with this interval. All right, let's move on to the next example, and I believe it's on the next page. So let's take a look at this. So let's enlarge this and see what we got. It says verify that f of x equals 1/4 x cubed plus 1 satisfies a mean value theorem. This time it's MVT on this interval right here that we're looking at from 0 to 2. Then find all numbers C that satisfy the conclusion. Okay, so what we got to do here is MVT. We got three things. First of all, is it continuous? Is F continuous on this interval, the closed interval from 0 to 2? Okay, looking at this polynomial, this is a closed interval. Yes. Step 2, is F differentiable on the open interval from 0 to 2? So f prime of x, this becomes 3/4 x squared. And yes, it's differentiable on that. Then I need to find all numbers that satisfy C, which is the conclusion of the mean value theorem. So what is the conclusion? That at some point the instantaneous equals the average. All right, what is the average? The average is f of b minus f of a all over b minus a. The instantaneous is f prime of c, and that's what I'm looking for, that value of c. So let's first start with finding f of 0. F of 2, right? Because this is f of a and f of b. All right, f of 0, when I plug 0 in, I get 1. F of 2, that's going to give me 2 cubed, which is 8 over 4, which is 2 plus 1, and I will get 3. All right, so there's my f of a, there's my f of b, and now let's plug these in. Oh, but what is my f prime of c? Well, we know what f prime of x is, so f prime of c is just 3/4 c squared. All right, so let's plug all our values in. 3/4 c squared equals f of b, which is 3, minus f of a, right in here I'm plugging it in, which I found to be 1, over 2 minus 0, right? This is b minus a. So this is your interval a to b up here, in case you've forgotten. So 3/4 c squared equals 2 over 2. So 3/4 c squared equals 1. So c squared is going to be 4 over 3. So c is going to be plus or minus the square root of 4 over 3. But I don't use both those answers, right? Why do I not use both those answers? So I've got an answer of root 4 over 3, and I've got an answer that is positive and negative root 4 over 3. Okay, this is a negative value. It is not in this interval, right? Square root of 4/3 is, I will tell you, approximately 1.1547. Okay, so it is not, this is a negative value. It's not in the interval. So choose only positive root 4/3, which is the 1.1547. So we're only going to choose that positive. So C equals this value. All right, let's take a look at the next example. And it says determine if f satisfies the mean value theorem on the given interval, and if it does, find C to satisfy the conclusion. All right, so we need to see if mean value theorem works on these. All right, let's see. And we need to find that final C if it does work. So let's take a look at this first one. Step 1, is this continuous? Is f continuous, f of x, on -1 to 1? Okay, can I plug in any value from -1 to 1 and will this work? Yep, it is continuous. Step 2, is f differentiable on the open interval from -1 to 1? All right, let's see. Over here, I need f prime of x, and that's going to be 1/3 x to the -2/3. If I rewrite this, this becomes, sometimes it's helpful to rewrite this, 1 over 3, the third root of x squared. All right, so is this differentiable on the open interval? Well, I can take the derivative at -1. I can take the derivative at 1 as well. But what, is there a value you can't take a derivative of? Yep, you can't. At x equals 0, this is undefined right here. So it's not differentiable at x equals 0. Therefore, MVT does not hold. It doesn't apply to this problem. We cannot use MVT on this problem because we can't take the derivative at a certain point in that interval. All right, moving on to the last example. Let's see if MVT will work on this. So we start with step 1 is f continuous on the closed interval, the closed interval 0 to 1. And can I plug in all values on the closed interval from 0 to 1 for this? Yes, I can. Okay, so yes, it's continuous. Step 2 is f differentiable on the open interval from 0 to 1. All right, let's take the derivative. Let's see if it's tricky like that first one was. This is 2/3 x to the negative 1/3 when I take the derivative. And I'm going to go ahead and rewrite this again. I'll put 2 over, this will be 3 times the cube root of x this time. Okay, oh, what about if I put 0 in? Well, I'm not putting 0 in because look, this is differentiable on the open interval, so I won't be using 0. Okay, so anything between 0 and 1, yeah, it works. This is differentiable. So step 1, step 2 work. So now we need to find the instantaneous equaling the average, and we know the average is f of b minus f of a. This is the tangent equaling the secant again over b minus a, and the tangent is f prime of c. All right, so the tangent over here I already know as 2 over 3 times the cube root of c, and this equals, let's slide this up a little bit, and this equals, all right, we got to find f of b, f of a. So when I find f of a, and this is f of 0, I get 0, and f of 1, I'm going to get 1. Well, that was kind of easy right there. So this will be 1 minus 0 over b minus a, which is 1 minus 0. Okay, that kind of worked out pretty nice. So over here, I will end up with 2 over 3 root c equaling 1. So 2 equals 3 root c. So cube, I forgot my 3 right there, 3 times the cube root, 3 times. So 2/3, I should have rewritten it like that, equals the cube root of c. Go ahead and cube both sides, so you get 8 over 27 equals c. Now you got to check, does this fall in the interval right there? So yes, so this is my f of c value, so this is what c will be. All right, that's MVT. Again, I encourage you guys to watch the follow-up video I have on this, how you'll see the MVT problems presented, but this was the basics. Remember, MVT is all about getting the tangent to equal the secant, which means getting the instantaneous, which is the tangent, equaling the average, which is the secant. That's what all MVT is, so don't let anything else confuse you. You just want the secant to be the tangent to be parallel to each other. All right? So thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.